Okay, so hi everybody. This is Science by the Slice. This series is produced by American Scientist Magazine. I'm the editor-in-chief, Vanessa Saunders. It's done in collaboration with science communicators of North Carolina, who helps us book our speakers and gives us our intern support. These are posted later as videos and with interviews. If you ever miss any, you can go back and find some. In addition, we get funding from the North Carolina Biotechnology Center and from the RTP chapter of Sigma Xi, who we appreciate. So thanks very much for coming. We have one more in this series in May, and then we take a break for the summer. But be aware that May 14th is also our alternate careers event that we're doing with the Biotech Center. So if any of you have interest in coming and speaking to graduate students about working outside of academia, let me know. I'd be happy to get you involved in that event. So today we have the real great pleasure of speaking with Andrew A.J. Kondash, who is a research environmental scientist at RTI Center for Environmental Health, Risk, and Sustainability. His work focuses on engaging diverse and underserved communities to help them evaluate and understand the nexus between environmental health and environmental science. So I'm gonna not read the whole thing. And we're gonna let you continue with your talk about the food, energy, water nexus. Thank you, Dr. Kondash.
Yeah, thank you all so much for attending. Today, we'll be talking about the food, energy, water nexus and a specific application of using oil field produced water, or OPW, for irrigation in crops in California. So to start off, what is the food, energy, water nexus, you might ask? It's the interconnection and interrelationship between energy, food, and water. So to grow crops, you need water. To power the tractors that keep the fields weed-free, you need energy. To produce oil, you need water. And it's all an interconnected circle. And so when we think about food, energy, water nexus research, there's really two schools of thought. There's natural resource management, which looks at quantity, availability, and access of these resources. And then there's an environmental health component, which looks at water quality, safety, and equity in providing these different aspects. And so there are different kind of focuses in each of these: environmental economics, resource government, food security on one side, food safety, clean energy, and safe drinking water on the other. And so why is this important? Well, it's really important to provide sufficient, safe, and sustainable food, energy, and water, especially with growing population and pending climate change and economic upheaval. Like I said before, climate change really exacerbates a lot of these natural resource challenges and really impacts resource access and safety, especially in areas that are prone to drought or lower water energy availability. So looking at this in California, we have an interesting case that hits on each of the food, energy, and water aspects. So California currently has the top agricultural sales of any state in the US with $42 billion annually. And that accounts for about 18% of total US agricultural production. A lot of the crops grown there are household staples such as wine, citrus fruits, almonds, and pistachios. At the same time, there is a really big concern about drought conditions in California. Extreme drought areas encompass most of California's arable land, and they're currently experiencing some of the most extreme droughts they've ever had in the past 10 years. They've had some of the driest winters in the last 100 years. And in December 2021, there was record snow, but winter drought and fast melting reduced snowpack, which severely limited water resources in that year. So here's just a quote from one of the rural farmers that talks about how they're in a really tough situation dealing with water quality and water quantity issues and making sure that they have enough ability to grow their crops and sustain their families. At the same time, oil production in California is also one of the largest in the United States. They account for about 4% of total US oil production. there are around 200,000 active oil and gas wells with 134 billion gallons of oil field produced water generated annually, and that stat is from 2018. So the real question we're trying to answer here is, can we mix the oil field produced water and use it to potentially be a solution to California's agricultural water problem? And then similarly, if we do that, what are the potential human and crop health effects of doing that? So looking in the specific county where we conducted this study, in Kern County, which is in Southern California, it ranks as the #1 oil producing county in the United States and contains about 65% of California's active oil and gas wells. And then you can see all these fun colored parcels are all different agricultural fields. So in addition to the prevalence of oil and gas, there's a really large impact of agriculture in the region. And so to help supply water for these regions, they formed what they call the Coelho Water District, which is a water district that supplies groundwater, surface water, and important for this study, mixes oil field produced water in with that water to irrigate their crops. And so zooming into the Coelho Water District, they've got a canal that is highlighted with the red line here. And the Coelho Water District and surrounding areas in this map, you can see 18,000 oil and gas wells. And like I said before, oil and gas produced water is currently being used to water crops in this region. So the study was a partnership between Duke University, RTI International, and the Pacific Institute, and was funded by USDA's NEFA grant from 2017 to 2020. And so the question we were really trying to answer is, what's the potential crop health and human health risks from using oil field produced water for crop irrigation? And so with this first study that I'm going to be talking about and presenting some results from, we go about the first question of what was the impact on crop. So potential adverse effects from OPW use on soil and plants. Some of the things we hypothesized at the beginning of the experiment was that there could be potential contaminant buildup within soil. Sodium buildup in soil could reduce infiltration or water's availability to move from the soil into the roots of the plants. Additionally, boron could potentially impact plants' abilities to conduct photosynthesis or help them grow. And then finally, the big concern is that contaminants could potentially accumulate in crops that people were eating. Yeah.
I'm sorry to interrupt. Is this water, the wastewater, treated before it's put into the crop?
Yeah, it's treated and blended with groundwater.
Okay. I just wasn't sure what kind of treatment happened after it came out of the wells, essentially.
Yeah,
Is that something you're gonna go into?
it's not. It's one of the things that the Coelho Water District has contracts with the oil and gas companies in the region, and the gas companies treat the water before they deliver it to the district. And so while we weren't able to get samples of like the before and after treated water, we were able to get samples of the blended water that we were able to analyze.
So this water, what is its source? Is it from fracking or?
No, so it's not from hydraulic fracturing. Most is conventional oil and gas drilling. So yeah, it's just you drill a pipe into the ground and suck out oil and water, and over time you get a lot of produced water from that.
Could you be more specific about what is in this water that you're putting on the plants? You mentioned boron, which I would guess.
Yeah, I'll get into that in a minute. Yep. Any other questions? So while we were there, we got some pretty amazing pictures of the different agricultural uses. So on the left, you can see in our Briar Creek case study where they were using 100% produced water straight from the well to irrigate crops. You can see a little sprinkler there watering a field. And then on the right is a picture from the Coelho Water District of, I think these are almond or pistachio trees, and they had a drip irrigation system that was directly connected to the Coelho Water District's soil or water system. So when we were conducting this study, we met with farmers to learn about their crop management practices and collect samples from their fields. we collected and analyzed irrigation water samples, soil samples from under almond and pistachio trees near their drip irrigation systems. And then we were also able to collect and analyze pistachio and almond samples directly from irrigated trees. So here you can see our site. There are the blue dots on this figure, a little bit hard to see, but in the top right is the Dwyer Creek Formation where I showed that first picture of the pretty arid looking area. And then the Coelho Water District is outlined by this red line, and you can see where we collected our samples within that. And then we got some baseline unirrigated soil and water samples from the bottom left regions of the screen. And so now I'm going to be showing a lot of box plots. So I figured I'd just give you a quick aside on how to read and interpret a box plot. So the things we're really concerned about are the median, which is that line in the very middle of the box plot, and then the maximum and minimum range and the interquartile range are highlighted by the box and the little whiskers on either end. And then any points outside of a box plot are considered outliers that are a little bit not really within the range of the data that you're showing. And so a box plot is a really good way to summarize a lot of data in a really small amount of space. And so, yeah, just looking forward, that's what we're going to be primarily showing for our results. So one of the things that makes produced water in this specific case a little bit different and readily usable for irrigation is that the salt and mineral content in the water is actually a lot lower than we would typically assume for a produced water. So for reference, the chloride concentrations in the Kern Front and Kern River formations, which are the two that are mainly used for irrigation in the Coelho Water District, are around 100 milligrams per liter. So just for reference, that's about what's in the water in your water bottles that you're drinking. And then the highest levels that we saw in the left side of this graph were in the tens of 20,000 milligrams per liter. And typically when you're thinking about produced water and the brines that come out of oil and gas production, we're thinking in the hundreds or several 100,000 milligrams per liter. So this is a little bit of an odd case of the produced water is actually pretty high quality compared to traditional produced water. And then just looking a little bit more into each of the different elements, I think that was one of the questions we had. Here's just a box plot with a log scale that show each of the different concentrations and the ranges of these contaminants that we observed. So a few things to highlight is there were a little bit higher boron concentrations than we were anticipating. Other things that were a little bit higher than anticipated were arsenic, a few other things. So looking at the soil that we actually collected, we really observed a minimal difference between the fields that were irrigated with the blended oil field produced water and groundwater supplied by the Coelho District, which are highlighted by the gray box plots here. The fields irrigated only with groundwater are shown by the blue box plots, and then unirrigated fields are shown by the green ones. And then the one key difference that we noticed in both the blended OPW and in that really arid case in the Dwyer Creek section were that sodium and boron, which are highlighted by the stars, were much higher in each of those cases than the groundwater irrigated or unirrigated systems. And so that kind of confirmed our hypothesis that the boron and sodium were some of the things that we were really concerned about when we were thinking about crop health. And so looking at this data, we found that the 90th percentile boron soil concentrations were above phototoxic soil benchmark of 0.5 milligram per kilogram. So this level is of potential concern for crop health because prolonged use can impact plants' ability to photosynthesize. Similarly, there's minimum difference between blended OPW and groundwater irrigated soils. And then looking at the crops that we were able to collect, these box plots show background levels that we observed in literature. So this is kind of the range that you would expect to see in typical crops. And then the gray dots show pistachios that we were able to collect within the Coelho Water District. And then we just went to the store and bought some local pistachios grown in the Central Valley, but not in the Coelho Water District, shown by the red triangles. And then we ordered a case of pistachios grown in Turkey in the blue squares. And so you can see from this that in all cases, we didn't really see a major movement of any contaminants or elements from the soil or the OPW into the crops themselves. And so a summary of this first half of the project was that the water in Kern County, the OPW, is of extremely high quality compared to more saline oil field produced water in other regions and of similar quality to the local groundwater. Additionally, using poor quality OPW can impact soil health, as we saw in the Dyer Creek example, and lead to the buildup of contaminants in soil and crops. And then finally, in talking with the farmers, we kind of understood that farmers know how to take steps to reduce impacts of boron and sodium accumulation in their soil. So one of the things they do is to apply gypsum to their fields, which helps bind out the sodium and boron from the water. And then they also try to plant crops that are a little better able to tolerate saline conditions. So again, pistachios and almonds are the prime example of that. So before we move into the next section, I'd be happy to answer any questions on kind of the soil and crop and water quality sections, if anyone has questions.
Just one quickie, I think you had mentioned that it was 100,000 milligrams per liter in the water that you had sampled, which is 3 times greater than ocean water. Why is that turning out that way? Is that just being extracted from the substrates it's going through?
Yeah, so the extremely high brines that we typically see in oil and gas produced water, the way oil and gas is produced is that in a lot of cases, ocean water and the creatures in the ocean will settle onto the bottom of the ocean floor. They'll kind of get trapped in sediment, and over time, the water will evaporate. And so you have that really high level of salt content in seawater. Most of the water evaporates and you're left with a really super concentrated brine that is kind of exponentially increases the level of salt in that water.
You didn't mention about the organic content.
Yeah, so I'm primarily an inorganic chemist, and so that was the focus of the quality. So one of the key things we were really kind of tagged as the next step on how to analyze this is doing more of the organic quality or the organic compounds in the water and soil content. All right. So the next question we wanted to ask is food irrigated with OPW in California safe to eat? And so what we did was we created a probabilistic risk assessment modeling framework. Now this looks extremely complicated, so I'm going to walk you through it kind of step by step in pretty simple terms. So the first thing we wanted to do was evaluate what we call the land-based source. And so we took data on local weather conditions, the water requirements to grow crops, the quality of irrigation water, and then the soil properties of the region. And putting all of that together, we created our land-based source model. And so again, the thing we were really interested in were the concentrations of inorganic compounds within the drinking water. And so comparing to drinking water standards, which are represented by this red line, any dots that we see above the red line indicate water above the drinking water standards. And then any dots or boxes we see below the line represent samples which were below the drinking water standard. So you can see in each of the different cases, we had a pretty good spread of data that was both above and below the drinking water standards when we evaluated it. Similarly, for primary, so those were primary drinking water standards or things that can primarily impact your health. So that we focus on antimony, arsenic, and lead in the water. And then secondary contaminants, which are usually mostly visual and aesthetic, can aesthetically impact water quality, so iron, manganese, and aluminum. You can see there's also a similar spread of data above and below the secondary and primary drinking water standards there. So putting all of this together, we were able to kind of estimate and predict the concentration of the different inorganic compounds within the soil that the crops were grown in. So next, we took that soil concentration and added the constituents or crops that we were trying to grow and the elements within them, and then the bioconcentration factors of each of the different crops. And so putting all of that together, we were able to create estimates of the concentration of the different elements in the food that people are eating. And then moving on to human exposure, we took food ingestion and incidental soil ingestion exposure rates, or basically how much food people eat in a given time period, and then how frequently they eat, and studied both adults and children in the study. And so that gave us a calculation for how much of each of the different foods or crops people eat and like a mass per time ratio. And then finally, evaluating all of this together, we evaluated different human health benchmarks, so a hazard quotient and a cancer risk assessment level based on EPA guidelines and benchmarks. And so just for anyone not familiar with risk assessment terminology, a hazard quotient is a ratio that estimates the potential for non-cancer health hazards from exposure to a contaminant. And so in cases where the HQ or hazard quotient is calculated to be less than 1, there are typically no adverse health effects expected from exposure. In cases where it's above 1, you would expect adverse health effects. And so for each of the different elements that we observed in our OPW, that was irrigating crops, we were able to kind of estimate the hazard quotient of children and adults exposed or eating those diets. And then we added an additional category for someone who eats a vegetarian diet primarily, so a little higher concentration of each of the foods that they would be eating would be coming from this region. And so as you can see in these, the hazard quotient of 1, which is the level where you would start expecting to see adverse effects, is highlighted by this red line. And none of the model runs really yielded any concerning results or hazard quotient values for each of the crops in vegetarian scenario for children and adults that were exposed to these crops. So then moving on, we also evaluated the cancer risk, which is a risk screening level expressing the likelihood of additional cancers being caused by exposure. So increasing risk by 1 in a million people exposed is shown as a 10 to the -6 risk. And then increasing risk by 1 in 10,000 people exposed is shown as 10 to the -4. So as the number gets higher, the risk of cancer gets exponentially higher. And so showing here a range of levels from 10 to the -6 to 10 to the -5, highlighted by kind of this red region, we can see that for both lead and hexavalent chromium, we don't see any higher level of added cancer risk, but then as I showed in the box plot, we have one of the whiskers for a vegetarian scenario where an adult could potentially have a excessive cancer risk there. So I've highlighted that with the circle in this figure. And then the other ones are really just outliers that fall within that range. And so shown in this figure, we have 90th percentile of food ingestion cancer risks. And yeah, you can see that the increased arsenic cancer risk for adults, assuming higher consumption of multiple foods within the categories grown within this region. And so focusing in on the arsenic, we show the kind of distribution of arsenic in the different water samples that we had. And so the arsenic maximum contaminant level is 10 parts per billion or micrograms per liter. And so I really should have put a red line here too, but you can see the median value for the blended OPW was a little bit higher than the arsenic drinking water contaminant level. And so that likely was the primary cause for seeing the elevated cancer risk. And so the main takeaway messages here are that first, low saline oil field produced water may be able to provide a safe, sustainable alternative to irrigation water. Especially if best management practices are followed, including adequately monitoring water quality and blending the water with local groundwater. Additionally, only a small percentage of OPW in California is currently used for irrigation. So this does have the potential to provide access to sufficient, safe, and sustainable energy, food, and water in the face of climate change and population growth. And especially if it's expanded to other regions throughout the state, throughout the state and United States, there are definitely additional concerns and would need to be more study on how this would be impacted by using higher saline waters. And so that kind of concludes what we've got right now. So happy to take any questions or answer anything anyone might have.
Thank you.
What percentage of the organizations that are utilizing this water are using best management practices?
Yeah, so we were only really able to talk to a few of the dozens of farms that were in this region, and each of the ones we talked to were using these best management practices. So it makes sense to extrapolate that most of them were, because they're pretty tight-knit community of farmers.
What kind of, you give me an idea of scale and the need for how, do they really need to add, they're running out of fresh water now, do they need to supplement? Like how, what's kind of the urgency?
Yeah, so when we were talking with the farmers, they were talking about how the water district isn't always able to provide water for them. And so a lot of them have drilled additional wells on their properties to supplement the water being supplied by the water districts. So from my understanding in our talks with farmers, the water districts weren't able to supply the full need of irrigation water for each of the farms within their regions. It was just kind of to supplement and provide as much as possible. But yeah, there's definitely a large need for this, and something that the farmers in the water district has been really pushing to increase this practice as much as possible. And so they used this study, and there was an additional study that was primarily focused on organics that were kind of the basis for continuing and expanding this. So that our goal in studying organics was to kind of fill in inorganics was to fill in the gap that was left.
Yeah, it was like following on to the earlier question, that would I mean, yes, I've been hearing regularly about the water problems in California, even though they're busy using more than their allotment and everybody else's, But are the USDA extension agents involved in this? Because that's where I was thinking about, like with the encouraging good practices. To what extent the extension agents would be covering both the water and soil quality as well as the crops.
Yeah, so California has something they call the basin plan that is a state regulated evaluation of the levels of contaminants within water that are allowed to be used for irrigation. And that's all published in collaboration with the USDA. And so they're all aware of this kind of need to potentially identify and use alternative water sources. And the basin plan kind of lays out the guidelines for how they can expand that use, and they're working closely with USDA to further impact and change those practices.
So the water they're getting from the oil wells, do you know how it's processed before it's, say, given to the agricultural use? And what's the cost in comparison? I assume the oil people are making money by selling this processed water?
Yeah, so the water is typically filtered, and in some cases they use electrolysis to remove particulate matter from the water. And so by doing that, you're able to remove a lot of the kind of heavier problematic particles in the water. But as far as the level of like selling and market for the water, I'm not really sure what the current deals or agreements with the oil companies are.
But the farmers would be buying it.
Are they, or is it a case of where they're obligated to deal with their own waste products? You know, so similar to like PFAS treatment here,
Mhm.
you know, where they're actually obligated to treat their own wastewater.
Yeah, so the way I understand it is that the water districts are kind of independent agents that are able to provide water to the farmers. I'm not sure what the like rates or how they would handle their like metering or charging water.
I had a question about the arsenic, since that seems to be the biggest problem,
Mhm.
at least in terms of health effects. I mean, regular sort of naturally occurring arsenic in groundwater is a common problem around the world. So is that something that could be economically treated because there's already systems in place for that?
Yeah, so going up to our actual results of the values we found in the plants themselves, one of the things that we observed in the model was projecting high concentrations of arsenic within the crops, especially pistachios. But it's not something we really saw in practice when we actually analyzed these results. And then additionally, the cancer risk screening level that we observed was the median level was well below the cancer risk screening level. And it was only the very kind of fringe top of the distribution. So for sure, there are concerns that potentially using areas with higher concentrations of arsenic could further exacerbate this problem. And it is something that's pretty easily treatable and removable.
Are you comfortable with extrapolating what you've learned from this one small area in California to other areas where there's oil extraction and then you have flood?
Yeah, so like I said before, the produced water here is a little bit different than you would observe in other regions throughout the United States. The lower salinity and lack of naturally occurring radioactive material observed in this water is something that makes it really effective or usable for irrigation. I would say in other regions, there could be alternative marginal water sources. So probably not oil field produced water unless it was of the type and quality that we observed in California, but definitely extractable to marginalized water sources like gray water or like municipal treated water or other sources that could potentially be used. But yeah, of course, those all would need their own kind of studies and evaluations to address the specific contaminants within those water sources.
One more question. So the wastewater obviously is one of the fields goes somewhere when it, even if it's not being used for irrigation. You said it's treated and then is it just released into the municipal like wastewater system, or what happens to it normally?
Yeah, so any water that's not used for irrigation, there's several different things or methods they use this marginal water source for. So in most of the United States, that water is injected into class 2 injection wells, which are basically just like reservoirs of really deep hypersaline groundwater. And so they just put basically the brines back in the ground where they came from. In some areas of California, they're using this produced water to help push saltwater intrusion from the oceans to protect groundwater aquifers. So they're using that as kind of a piston to push that water through. And then in some cases, they're using the they're recycling this oil field produced water in what they call enhanced oil recovery. So they'll drill a hole and then use the produced water to push oil and gas from nearby wells up through one of the central wells. And so that's a very water intensive process. And if they're able to use marginal water sources, they're able to kind of reduce the impact of water quality there.
Any other questions for us? Great, thank you so much. Feel free to come up and talk.